So, hi all, continuation of the module 2 multi-carrier modulation. Today let us discuss about the OFDM block diagram and how that OFDM is going to be used in the LDE, that is long-term evolution. So this is the block diagram for the orthogonal frequency division multiplexing. In the diagram itself, it's very clear that I will give the overview of the block diagram here. X input is given to the L point inverse discrete Fourier transform, and it will be converting into the X samples. After this, it is given to the parallel to serial converter. Then we are adding the cyclic prefix, then the channel, that is H of n. Then we are giving to the adder, along with the adder the output of H of n. We are introducing a noise n. Then that is, so output of it called as y is equal to h into circular convolution of x plus n. This x plus n. Now we are deleting the receiver side, we are deleting the cyclic prefix, then serial to parallel converter, so we are getting y. So the output of serial to parallel converter will be y is equal to h into circular convolution of x plus n. Then we are giving to L point discrete Fourier transform. So y, then it is forward error correction, then x cap. Okay, so let's see one bit. First it is in the transmitter operations. First step, what we have seen, we are giving to inverse discrete Fourier transform, but basically we wanted to break a signal of bandwidth into L narrow band subcarriers. Okay, so that subcarriers bandwidth will be represented by B by L, and this subcarrier will experiences with the flat fading, or we can say it is a inter-symbol interference free communication. Okay, so the cyclic prefix will exceeds the delay spread is used. Now we can give some representation. The L subcarriers for a that given OFDM symbol are represented by vector X, which contains the capital L of current symbols. So that is dividing a narrow band into L. Now we have obtained a L independent narrow band subcarriers are created using an IFFT operation. That is step 2. Now coming to the step 3, what this ISI channel. Now we are decomposing the ISI channel into orthogonal subcarriers. We are adding a cyclic prefix, right? In the diagram we have seen, we are adding a cyclic prefix of length V. Then the resulting will be L plus V symbols, or then it will send it to a serial through the serially, that is parallel to serial converter, to send serially through the wideband channel. Coming to the receiver operation. Okay, so actually in the transmitter, whatever the process we have taken, that will be done reversely in the demodulation. Actually, demodulation is nothing but recovering of original signals. Okay, so that if we coming to the receiver operations, first we'll see the diagram once. Here we are added cyclic prefix. Okay, so after the summer it is deleting the cyclic prefix, and in the transmitting side we are using parallel to serial converter, but in the receiving side we are using serial to parallel converter. So all the transmitting process will be in the reverse process. So coming to the receiver side, the cyclic prefix will be get discarded, so that L received symbols are demodulated using an fast Fourier transform operations, and this fast Fourier transform operation is result in the capital L data symbols and this capital L data symbols are in the form of YL is equal to HL into XL plus NL subcarrier L. So this is the formula mathematical expression we are going to use, and this each subcarrier can then be equalized through FAQ by simply dividing by the complex channel gain H of I for that subcarrier. So it is given as like this: XL bar is equal to X1 plus N, which is the dividing the complex channel gain. Okay. Now, orthogonal frequency division multiplexing in long term evolution. Here there are two domains it will be used, that is time domain as well as the frequency domain. Whenever the input to the L independent, that is quadrature amplitude symbols, that is the vector X, and these L symbols will be treated as separate carriers. So this is the block diagram, that is how it is working in the time domain as well as the frequency domain. Here we are giving a quadrature amplitude modulation symbols, okay, to the inverse Fourier transform, and also okay, and in that L point IFT it will create the time domain L vector X, that is cyclic extended to the length L into 1 plus G. Now this G is nothing but a fractional overhead. In long-term evolution the value for G is 0.07. For the normal cyclic prefix the value of G is equal to, that is G is equal to 0.07, and for the extended cyclic prefix G is equal to 0.25. Okay, so in the diagram if you see here, it is created the time domain along with the cyclic prefix of LG samples is also added, and here we are introducing the factor G. The formula itself, speed is equal to V by L hertz, and L into 1 plus G samples, it is created by inverse fast Fourier transform, and the cyclic prefix G value is G is equal to 0.07 for normal cyclic and 0.25 is for extended cyclic. Now this is given to the parallel to serial, will converted into a wide digital signal. Okay, the amplitude modulated with the carrier frequency of C is equal to WC divided by 2 pi. Okay, if you see the diagram will come to know. So here we got that WC, it is C divided by 2 pi, the parallel to serial converter. So now the serial stream we have got is B into 1 plus G of hertz. Now we are going to give this into digital to analog converter. So this digital to analog converter, we already know that so in the digital to analog converter, what is happening in the sense, the digital to converter, the digital signal will be converted into the continuously time varying signal, so that we will get the X output in a proper way. So these are the things happened in the orthogonal frequency division multiple access in long term evolution. Hope everybody understood the OFDM in block diagram as well as the OFDM in time and frequency domain. Thank you.